Hello everyone, another video. Today we are talking about electron configuration. So we're still in Unit 1. We are in Essential Knowledge B and Enduring Understanding 2, or vice versa, whatever. But it's Unit 1, concept, the second concept, and we're about halfway through it. Electron configuration. Electron configuration is very important to know the basics of, but it's not very important to know the details of. And we will do a little bit of the details in class, but we're not going to spend a ton of time because it just kind of works out to be rote memorization, and as long as you know the general concept, that's usually good enough. So electron configuration describes how electrons are arranged around the nuclei. Okay, so it describes both the distance the electrons are, and also just kind of the shape and location they are in the nuclei, or around the nuclei. So it describes how electrons are arranged around the nucleus. The electrons are first of all in shells, and shells are another term for energy levels, so you may hear it in shells, first shell, second shell, third shell, or you may hear it in energy level 1, energy level 2, energy level 3. I tend to call them energy levels just because that's how I was taught way back when. One's not right, one's not wrong, it's just different terminology. So they're in shells or energy levels. The higher the energy level, or shell, the farther from the nucleus. So if we were to have a picture of an atom here, let's call that the nucleus. The farther from the nucleus, the higher the energy level. So, for example, this would be energy level 1. Okay, so that's energy level 1. And now this one might be energy level 2. Okay, and that's a really horrible one because it's kind of oblique. They are roughly kind of circular on energy level 3. Kind of get where I'm going. And I tried to make it colorful because colors are fun. Excellent. Okay, now it's important to realize that the distance between energy levels, so between 1 and 2, let me do it this way, between 1 and 2 and 2 and 3, the distances do grow. So energy level 1 is very, very close to the nucleus. Energy level 2 is slightly farther apart. Energy level 3 is much farther apart, and 4 and so on. It's almost exponential how far apart the energy levels become. So energy level 7 is extremely far from the nucleus. And that's why most scientists agree that we're going to hit a lull in discovering new elements, or creating new elements. We've kind of hit the end of energy level 7. And in order to create an element for energy level 8, it's going to require vast advances in our science knowledge and technology. So we've kind of hit a little bit of a lull. So don't expect the periodic table to change too much, but I'm sure it's not impossible, and I'm sure eventually it will. Okay, within these shells, within these energy levels, we talk about orbitals, or subshells, and that describes the shape of the electron's orbit. Okay, and these are given letters. So, let's say we're talking about electron configuration. I'll use green. And electron configuration looks something like this. 1s2. Okay? That 1 is the energy level. That s is the shape. That s is the shape. And that 2 is how many electrons there are that make up that shape. So, if we have our nucleus here, the s shape is spherical. S doesn't stand for spherical. It's kind of coincidental the way that works. So that means that around this nucleus, these electrons are going to be somewhere in this kind of cloud-like shape. That's going to be roughly a circle around that nucleus. And they could be anywhere within there. Okay? Now, this cloud-like, and you know how clouds don't have definitive edges? Energy levels don't really have definitive edges either. What we draw as the edge, that's where the electron spends 95% of its time. It spends 95% of its time in there, and we just kind of cap that at the edge. But just like clouds, once in a while you might have a couple of, the electron might venture outside, okay? But it spends 95% of its time within that area. And that becomes important because as the shapes get more complex, like for example, the second energy level has a P, all right? P is more of a dumbbell shaped. And there are 6 electrons that make up that P. So, if our nucleus is here, they kind of make up a dumbbell shape like this. And it spends 95% of its time within this dumbbell shape. And then it has another dumbbell shape here, where it spends 95% of its time. And then there's another dumbbell shape on the z-axis coming out at us. But as you can see, I can hardly draw 2 dumbbells, let alone that third one coming out and going back into the board, kind of doing this thing. So it spends 95% of its time in these shapes. So 5% of the time it does not conform to that shape because these are, they're called almost like electron clouds is the newer term. Newer being only 50 years old. So it's the newer term, the electron cloud, and that's because it's only 95% of its time. However, that's about the best we can do because electrons are traveling ridiculously fast and they are ridiculously tiny. And anytime you try and find an electron, you end up shooting it to a different spot in the atom. All right, it's almost impossible to know. It is impossible to know where it is and where it's going without altering its trajectory. All right, if that makes any sense. So these are electron clouds. It spends 95% of its time in these shapes. And that's why we're not going to spend a ton of time memorizing configuration. It's just kind of important to know that electrons travel around the nucleus. They travel in distinct areas around the nucleus, both distance-wise and shape. However, they don't have to conform to that. They can move around slightly. Okay? So we're going to go over the details of electron configuration in class. I'll show you how to write the electron configuration. Very, very quickly, it follows a filling order. You always start at the beginning, and once you've filled that energy level and orbital, you move on to the next one. The filling order, roughly, well, not roughly, exactly, is this. I think so. All right, and it keeps going, and then you hit actually 6s2, 4f14, 5d10, 6p6. Okay, so it kind of keeps going. It starts off kind of this regular 1s2, sp, sp, s kind of pattern. Remember, these are the energy levels, these are the shapes, and these are the amount of electrons. And then it kind of gets funky around the D block and the F block. Because those shapes are so complex, it actually takes more energy. So, for example, notice 3d10 right here is sandwiched right in the 4 energy level. So it takes less energy for the electrons to be in the 4th s orbital because it's simpler than in the 3d orbital because it's more complex. And it has to do with, like, it looks like a dumbbell with kind of a donut going around it. Almost something shaped like this. I can show you pictures in class of that because that's a horrible picture. But anyway, so that's such a complex shape that it's easier to go farther from the nucleus and just have a simple spherical cloud. So that's kind of why. We don't really worry too much about this filling order just because it would be rote memorization, and what's the point? It doesn't really do a ton. What is important about the electron configuration isn't necessarily the exact configuration, but to realize that there's differences in electrons. Not all electrons are created equally. In fact, let me erase this entire thing. I want to talk about shielding. Okay, I want to talk about shielding. So shielding occurs between core and valence electrons. Okay? Between what we call core electrons and valence electrons. So now let's talk about a little bit of terminology. Valence electrons are the outermost electrons. And by that I mean the outer energy level. Outer energy level. I did that very weird abbreviation. I don't know why I made it a capital L, but I was running out of board space. So valence electrons are in the outermost energy level. They're the far outer regions. Okay, so if you're thinking about olden days United States, they'd be like the western, right? They'd be in the Wild West. They'd be one with like the sheriff walking into town. They're the valence electrons. They are far from the nucleus. Okay, they are far from the nucleus. Then obviously, hopefully you deduce that core electrons are not the valence electrons. Meaning they're in the inner energy levels. Okay, so they are in the inner energy levels. So they are closer to the nucleus, and more importantly, there are electrons farther out. There are electrons with more energy out there. What ends up happening, shielding, occurs when the core electrons shield the attraction of the nucleus to the valence electrons. So what happens is shielding is when the core electrons shield the attractive force between the nucleus and the valence electrons. They act as a shield between the nucleus and those valence electrons. So if I have a nucleus here, and I have some valence, or I have some core electrons represented in green. These are my core. These valence electrons out here, they're not going to feel that coulombic or that attractive forces we were talking about in the last video. Because this nucleus, this positive charge here, it's going to hit these electrons, and it's going to hit almost like a negative wall. It's going to pull those electrons in, but it's going to hit almost a wall, and those electrons are going to absorb much of that force. Because if you think about it, if I have an electron here and a valence electron here, this electron, this green electron, is actually negative. So it's going to emit a negative repulsive force, right? It's going to emit that negative force, and that's going to cause that valence electron to be pulled farther away. All right, so it's going to cause that valence electron to be pulled farther away, or rather, not feel as much of that core attractive coulombic force. Okay, so that is shielding and electron configuration. Good luck, and I will see everyone in class. Thank you.